Welcome back to the course again. So today what we want to do is we want to solve the problem of making the ship smaller. That is, we want to, for testing and experiment purposes, we want to convert this huge ship into a small testing model which will show the same behavior as this huge ship. Of course, you cannot have a huge ship lying around your lab to test, unless you have a really huge lab, which is the sea itself. But generally we have a small laboratory which is size of a big hall. You have a wave pool there and you want to test your models out there. So you want to find out certain similarity parameters so that you can enlarge or shrink your ship to whatever extent, but it will show the same behavior as long as those similarity parameters are met, right? So therefore we'll talk about the similitude, which is nothing but the similarity ratios which we want our ship models to agree with. So there are a couple of different similitudes. For example, there is geometric similitude, there is kinematic similitude, there is dynamic similitude, and if you go on, you have internal constitutional similitude, boundary condition similitude, and so on. But for our purposes, we'll just focus on these three main types of similitude and what are the similarity parameters which we need to consider. So geometric similitude, we have done this in our 10th grade, ninth grade, which is nothing but, suppose you have a triangle and those two triangles are similar, and you have one of the lengths given in this triangle, you want to find out the other length, right? So you can do that by the similarity principle. Here I've just doubled both of them. So that is the geometrical similitude. That is, they should be geometrically similar, which includes the length ratios, which we just did here, which is 1:2, and the angles also it could be. Then we have the kinematic similitude, which will involve the displacement ratios or the velocity ratios. Right. So it could be that if the ship travels at 2 meters per second in the wave pool in your laboratory, it then the in the actual scenario it will travel maybe at, let's say, 2 kilometers per hour or something. Okay, that's too slow speed maybe, but you get the point, right? If it's 2 meters per second here, it could be something else there, depending upon the similarity ratio which we find out. Then you have the dynamic similitude, which involves the force ratios, stress ratios, and pressure ratios. Because of course we have seen above too that the Navier-Stokes equation depends upon the body forces and the stresses, shear stresses, and right, acting on the fluid particles, and therefore these ratios should also be met in order for a complete model which will simulate the actual ship, and that's our main aim to do. So we have couple of theories to find the similarity parameters or the similarity ratios. So the first one coming up is the Buckingham's pi theory. It's the BUCK, Buckingham's pi theory. It has nothing to do with 3.14. It has nothing to do with pi. So what this theory says is that suppose we have dependent some variables, let's say x1, let me write that. So we have x1, x2, x3, and so on. We have many variables like this. Maybe they are dependent or independent. What our aim is, we want to, this is not 3.14 again, it's just a notation. So we want to find out pi, let's call this as the ratio. And of course we know an important property of ratios that they are dimensionless. They have no physical dimensions like length, mass, time, etc. So they are dimensionless. So this is a really important tool which we can use to derive these similarity ratios. So we have x1 raised to alpha 1, x2 into x2 raised to alpha 2 into x3 raised to alpha 3, and so on. So what we want to do is we want to find out alpha 1, alpha 2, alpha 3 in such a way that all these equations should turn out to be dimensionless. So suppose, for example, let's say we have pi equals to let's say it's force times length. Now we know that force consists of, so we want force into alpha 1 and length raised to alpha 2 should be a dimensionless quantity. So force we can write down as it's just nothing but mass into acceleration, which is meters per second square. So this raised to alpha 1 into L raised to alpha 2 must be dimensionless, which means that m raised to alpha 1 into L raised to alpha 1 into t raised to minus 2 alpha 1 into L raised to alpha 2 must be dimensionless, which means that alpha 1 equals to 0, so that we don't have any mass dimension. This also proves that alpha 1 is already 0, then this also alpha 2 must be equal to 0 similarly, and thus we have these two solutions for the dimension less quantity which we want to derive. So we can write that constant is equal to f raised to 0 into L raised to 0. Of course this doesn't make any sense, and therefore we don't actually get a dimensionless quantity. We can substitute alpha 1 alpha 2 to be 0, but that would be of no use. Coincidentally it came out to be 0 in this case, but in other cases where you have a lot of parameters, it's not necessary it will turn out to be 0. You'll get some linear equations maybe in alpha 1 alpha 2 alpha 3, and then you solve them to get different solutions for them. So I hope you're getting an idea right now of how do we derive these equation parameters. So your xi or x1 x2 x3 could be anything. It will be the basic parameters which we have, which could be a constant, mass, length, time, etc., whatever you have it, right? So those are the basic parameters. Those parameters could also be raised to some power, and then you are just raising it to alpha 1, multiplying it by another x2 x3, and then you want it to be dimensionless, and therefore you solve it for alpha 1 alpha 2 using the linear algebra which you have learned. So that's it. That's the simplest thing which we are doing to obtain the similarity parameters. Then the second law which we have is the model law, and let's not talk about the model law in greater detail. It's nothing but it's kind of a advanced version of the Buckingham's law. So model law is nothing but that the similarity parameters of the model must be equals to the similarity parameter of the prototype. And one more thing to notice, suppose you get a similarity parameter, let's say the similarity parameter is pi, then another similarity parameter which you can simply derive, this is pi 1, is pi 1 raised to minus let's say 2 into pi 1 raised to minus 1. This can also be a similarity parameter, because if this is dimensionless, this also has to be dimensionless, right? So that's just simple math which we just did. And let's actually get things clear by taking an example of deriving these similarity parameters. So let's say you have a cylinder or sphere and the diameter is d, all right. Then I have body forces acting, let's say this is F, and then I have the velocity of the fluid u, and let's say we have the density rho and the velocity v. So this is the u is nothing but the fluid velocity, and v is nothing but the viscosity, not the velocity. So this is the velocity, this is the viscosity, and we are talking about incompressible flow. Incompressible flow. And what we can do is, let's say we have to find a similarity parameter which should depend upon these parameters, which is f, d, u, rho, and the viscosity. So pi is equal to f raised to alpha 1 into u raised to alpha 2 into d raised to alpha 3 into rho raised to alpha 4 into eta nu raised to alpha 5. So these are the this is the similarity ratio which you want to find out. And what is given is, of course, force in its core, is nothing but ml t raised to minus 2. So the mass, length, time, and so on are the basic fundamental physical quantities which we have. So this force, velocity, the diameter, these all are nothing but a combination of different fundamental physical quantities. So let's say we also have a table given here. So let me just quickly copy paste the table. All right. So we have this table given here. Let me showcase it here. And this table is for p equals to 3. Now p is equal to 3 is nothing but let's say you have the parameters. So you have xi. Now these three are nothing but they are function. They are some combination of mass, length, and time, right? So here we have three different parameters here. So p is equal to 3, and here it's just a table representation of the mi is what for force. So force I can write down as some constant which I'm going to assume 1 into uh, m raised to 1 which is from here. Then we have length raised to L raised to 1 again, which is here, and T raised to -2. So here we have the dimensional analysis for force. In a similar way, we have for the velocity, for the diameter, etc. Now what we want to do is we want to write this down, pi equals to the same equation. So I'm not writing that down again. So if we expand this equation substituting these quantities, what we are going to get is pi 1 equals to C1 into C2 into C1 alpha 1 into C2 alpha 2 into C3 alpha 3 into C4 alpha 4 into C5 alpha 5. So this comes down from these constants which we get from each individual parameter which we have here. So these are the constants. I'm going to write that in one bracket. I don't care much about the constants here because constant is anyways dimensionless, so it's of no use solving for them. Then what I'll have is I'll have m raised to mi alpha I, right? Mi alpha I, L raised to Li alpha I, and so on. So at the end what I want to find is that the alpha I mi which I get must be equal to 0, the alpha I Li which I get must be equal to 0, and of course you have T raised to alpha I Ti which should also be equal to 0, the summation of everything which we got. This is the Einstein notation. This signifies summation alpha I mi from I equals to 0 till let's not say 0, let's say I equals to 1 till 5, because we have the 5 different parameters here: F, U, D, rho, and viscosity. So this is what we need to solve, and as you can clearly see, this is nothing but a linear algebra problem. So you kind of have how many equations do you have? You have 4 equations. Sorry, you'll have couple of equations. You have 3 equations over here, and the variables which you have will be kind of alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5. So those are the 5 variables which you will have, and you can write this down in a matrix format if you have done some linear algebra problems involving matrices. You can write this whole equation in a matrix format. Let me just copy down as well so that we don't waste time writing it. And here we have it. So this is nothing but this table which I have got. This vector, this matrix is nothing but a representation of this what we had in terms of alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. We multiply these two terms and they should be equal to 0. They should satisfy this equation. So that is what we have written in linear algebra format. If you're not clear with this, you can probably go back and revise the series and matrices chapter. So this is what we have done, and now we can solve this. And also if you see the rank of this system which we have is 3. So we have 2 non-trivial solution, which means that if I fix alpha 4 and alpha 5 for any any random values, if I give alpha 4 and alpha 5 any random values, then the values for alpha 1, alpha 2, and alpha 3 will become fixed. So this is something interesting which we got, right? So suppose, let's say for our first scenario, let's choose that alpha 4 equals to 1 and alpha 5 equals to 0, and let's say we solve this equation. So we'll get 1 0 0 0 1 0 0 0 1 into alpha 1, alpha 2, alpha 3. Note here that it's not an equation of alpha 4 and alpha 5 because we have fixed them already. So this should be equal to -4 4 2. You can just solve out this equation to get this, and from here you can have a solution for alpha 1, alpha 2, alpha 3, which you'll, so you just need to take the inverse of this, multiply this side and so on. So that's just the maths which we are not interested right now. So this will give us the alpha 1, alpha 2 and alpha 3 as let's say -1, 2 and 2. So this is some solution which we got, and now we can write pi 1, or the first similarity ratio which we got, as f raised to alpha 1, which is -1, u raised to alpha 2, which is 2, and d raised to alpha 3, which is 2, and rho raised to alpha 4, which we chose as 1, and viscosity 0. So this is what we have. This I can write as rho u square d square by f. So this is actually a used similarity ratio which we use. By convention, I can say that pi 1 is similar to 2 pi 1 raised to -1. This is of course again a dimensionless quantity, and by convention we write pi 1 as f divided by half rho u square d square, which is equal to CD, and this is known as the drag coefficient. So this way we derived the drag coefficient, which is widely used in aerodynamics or hydrodynamics to calculate the drag which can be acting on a body, in this case a cylinder or any body with diameter d. And you just looked at the process of how do we derive the similarity parameters, and now you have a clear understanding of how you can derive other parameters as well. So in our next lecture, we'll use the Navier-Stokes equation to derive some other really important parameters which we will be using, and which help us in practical engineering to scale down or scale up our model accordingly. So this was the drag coefficient. Next class we'll look at the Froude ratio and other kinds of ratio. So till then, stay safe and thank you.